Welcome back. Today, we're diving into an absolutely fascinating explainer based on a recent eye-opening piece from the MIT Technology Review. We're all pretty used to AI helping us draft emails or maybe, fix our grammar. But today, we're looking at a monumental shift. We're moving from a world where AI is just a helpful digital assistant to one where it's literally putting on a metaphorical lab coat and stepping in as a fully autonomous colleague.
So it begs the question, is AI just a tool, or is it actually becoming a co-researcher? It's a profound question, right? And it's no longer science fiction. We are right in the middle of an incredible paradigm shift happening in laboratories worldwide, literally as we speak. The answer to this question could completely redefine how human knowledge expands, and the stakes honestly could not be higher.
Okay, let's dive into this. Here is our roadmap. First, we'll cover the birth of the AI scientist, followed by the intense development race. Then, we'll look at agent collaboration, trace their leap into the real lab, and finally, we'll unpack the risks facing science itself.
All right, kicking things off with Section 1, the birth of the AI scientist.
To really understand what's happening right now, we first need to look at the ultimate ambition driving the major tech companies. They're making this grand promise to the public and to their investors, frequently pointing to the potential for AI to drive massive scientific breakthroughs, things like curing cancer or solving climate change. This is essentially the holy grail that tech giants use to justify the immense resources required for the AI ecosystem we interact with every day. Because if an AI can eventually cure a complex disease, well, the logic goes that it suddenly justifies the enormous carbon footprint of data centers and the flood of low-quality AI-generated content we see online.
But let's take a step back and look at where we actually are today. Right now, large language models essentially act as an invisible coworker. They're already great at finding relevant research literature, drafting academic papers, writing code. They handle the mundane, time-consuming tasks. But make no mistake, a massive promotion is currently underway for these systems.
And this brilliantly illustrates the dizzying pace of recent breakthroughs. The defining moment really arrived back in 2024 when Google DeepMind's Demis Hassabis and John Jumper won the Nobel Prize in Chemistry for AlphaFold, which is a specialized AI that predicts protein structures. That victory basically fired the starting gun. Barely a year later, in October 2025, companies like OpenAI and Anthropic launched specialized biological models. And by February 2026, we saw the introduction of models like GPT-Rosalind seamlessly integrating with actual lab environments.
Which brings us to Section 2, the intensifying development race.
That Nobel Prize we just mentioned was really just the spark. What followed in late 2025 was a full-blown corporate sprint to dominate this new field. A perfect example of this race is GPT-Rosalind. This was introduced as OpenAI's first expert science model. Both OpenAI and Anthropic are aggressively building specialized science teams to reach what they call their North Star. And actually, that North Star isn't just a slightly smarter digital assistant, it is the creation of fully autonomous researchers, capable of planning and executing complex projects with minimal or even zero human intervention.
Moving right along to Section 3, agent collaboration.
Now, what's really interesting about this slide is how these autonomous researchers actually function. Transitioning from corporate strategy to actual software architecture, check out the workflow here. These systems don't operate as one giant monolithic brain. No, they operate as a team. Google's co-researcher tool, for instance, uses multiple specialized agents to mimic a real human scientific team. A supervisor agent receives the overall goal from a human scientist. Then, generator agents brainstorm hypotheses and design research plans. Finally, ranker agents interpret the options and decide on the absolute best course of action. It's literally an entire virtual laboratory team working in perfect sync.
And the crazy thing is, this isn't just theoretical. The MIT Tech Review highlights a fascinating, tangible anecdote from James Zhu's AI for Science lab at Stanford University. They created a virtual lab using this exact multi-agent structure. By having different AI agents act as experts in various scientific fields, this virtual lab successfully designed a completely novel antibody fragment capable of binding to SARS-CoV-2, the virus responsible for COVID-19. So they're already successfully tackling very real, very complex threats.
All right, let's look at Section 4, into the real lab.
Because no matter how brilliant a virtual lab is, science eventually has to interact with the physical world, right? To understand how these virtual minds are being placed into physical robot bodies, look at the comparison we have here. On the left, we have virtual agents. They are incredible at formulating hypotheses up in the cloud, but they hit a wall because they can't physically test them. On the right, we have physical robots, which can execute experiments flawlessly but traditionally need strict, step-by-step human programming. The massive breakthrough happens when you connect the two. Plugging large language models directly into physical testing environments unlocks a totally unprecedented level of automated discovery.
And we saw this exact milestone hit in February 2026. According to the source, OpenAI integrated GPT-5 directly with Ginkgo Bioworks' Automated Biology Lab. Think about what this actually means. The AI doesn't just suggest an experiment anymore. It proposes it, the robotic lab executes it, and the AI then immediately interprets the fresh data to propose the next experiment. It is a continuous, iterative loop that minimizes human intervention while absolutely maximizing experimental output.
So, what was the result of that specific integration? 40%. That number represents the dramatic reduction in the cost of synthesizing a specific protein, achieved entirely by this AI and robotics collaboration running a massive number of experiments. It's a staggering efficiency gain that proves the commercial and scientific value of this technology out there in the real world.
Finally, let's look at Section 5, the risks facing science.
Let's ground our enthusiasm for a second and shift to look at some systemic warnings outlined in a recent study published in the journal Nature. So, the crucial point is understanding the trade-off here. There's a deep tension between the individual researcher and science as a whole. For an individual researcher, adopting AI provides a massive competitive advantage, accelerating their career, their publications, their output. But the Nature study warns that this might inadvertently harm the wider scientific ecosystem by causing a severe loss of diversity in what actually gets researched.
They call this the homogenization risk, because AI systems are fundamentally trained on huge amounts of existing data and literature. They naturally favor and excel in fields that are already data-rich. The risk is that researchers will naturally gravitate toward these AI-friendly areas to boost their own success. This leads to the neglect of niche problems or completely new, less data-rich fields. Ultimately, this narrows the overall scope of human scientific inquiry, potentially leaving researchers who study unique, complex, but data-poor problems out in the cold.
The source material summarizes this warning perfectly with this quote from the study. Maintaining the vitality and diversity of science in the AI era requires coordinated organizational effort by the scientific community. The vital takeaway here is that technology alone just isn't enough to guarantee good science. Human coordination, institutional policy, and deliberate, thoughtful effort are absolutely crucial to protect scientific diversity as we integrate these incredibly powerful tools.
Which brings us to our final, provocative question for this explainer. Are we actually ready to share the lab bench? The technology is moving from digital assistants to autonomous, robotic co-researchers at breakneck speed. The potential to solve our greatest challenges and invent the medicines we might take in the future is right there for the taking. But so is the risk of fundamentally altering the nature of scientific discovery itself. It is a fascinating time to watch this space unfold. Thank you so much for joining me today, and I hope this gives you a clearer, structured picture of the new era of the artificial scientist. Keep questioning, keep learning, and I'll catch you next time.